Many types of equipment have a rotating shaft that penetrates a stationary housing. In cases where the equipment moves a fluid, some material or device is needed to seal around the shaft to keep fluids from leaking out and contaminants from getting in. Sometimes packing material is used to seal around the shaft, but most equipment that uses packing requires a small amount of leak-off to reduce friction between the packing and the shaft. So in applications where leakage needs to be prevented, mechanical seals are often used. As a mechanic, you'll need to understand how mechanical seals work and how they're installed. Mechanical seals are often used in applications where leakage around a shaft needs to be prevented. For example, they're often used on pumps that handle hazardous fluids. Mechanical seals can be divided into two basic categories: pusher type and non-pusher type. These categories are based on the ways in which the seals allow the rotating ring and the seal between the ring and the shaft to move along the shaft so that proper clearances are maintained. Although mechanical seals are designed to last a long time, some of them fail well before their life expectancy is reached. One of the most common causes of seal failure involves problems with the equipment that the seal is installed on. For example, misaligned shafts, bent shafts, or bad bearings could easily cause a mechanical seal to fail. Sometimes, however, mechanical seals fail for other reasons. Another way that the seal face gap can widen is if either seal face becomes distorted or warped. One cause of seal face distortion is over-tightening the gland bolts during installation. Another cause of seal failures is overheating. Heat is often a part of a machine's operation, and mechanical seals are designed to function under those conditions. But sometimes the heat becomes so severe that the seal parts begin to break down. The seal faces may also be attacked by the fluid that's being sealed. One way to tell if this has happened is by examining the seal faces for damage. The materials used to make the seal faces are generally corrosion resistant, so corroded or pitted seal faces could indicate a chemical incompatibility problem. Another cause of seal failures involves the improper installation of the seal. One of the most frequent installation problems has to do with the positioning of the rotating element. If the rotating element isn't positioned properly, the seal will almost certainly fail prematurely. The mishandling of seal components before and during installation can also lead to seal failure. The seal faces are among the easiest components to damage by mishandling because they're usually quite brittle. However, some mechanical seal components can be damaged because they're relatively soft. For example, during installations, O-rings or bellows are sometimes cut by sharp edges on the shaft, such as shaft shoulders or shaft keyways. The causes of mechanical seal problems that we've just covered should give you an understanding of why seals fail. When a defective seal is replaced, it's often possible to examine the seal's parts to find clues for the source of a problem. For instance, it may be possible to identify causes of some seal problems by examining the wear patterns on seal faces. Before a mechanical seal can be installed, certain preparations have to be made. These preparations typically include disassembling equipment and removing the damaged mechanical seal. Since one of the most common uses for mechanical seals is in process pumps, we'll use that equipment as an example. Our demonstration takes place in a seal manufacturer's training facility, but you'll probably install mechanical seals in a shop or where the equipment normally operates, so you'll need to follow some general precautions to ensure that the seal can be installed properly. For example, the work area and the pump housing should be cleaned. Also, company policies and procedures, as well as the appropriate safety precautions, should be followed. One of the first steps is separating the casing from the pump frame. To do this, the casing bolts must be removed. Then jacking bolts are installed to force the casing and pump frame apart. The jacking bolts are turned in a crosswise pattern to evenly dislodge the casing from the frame. Now the frame and the bearing housing can be moved to the side to allow for easy access to the remaining parts. The jacking bolts are also removed. Then the old casing gasket is taken out and discarded. A new gasket will be installed later. Next, the impeller is removed, and so is a small impeller gasket. The backplate is match marked with the frame to make reassembly and alignment of the components easier later on. Then the backplate can be removed. First, the nuts that hold the backplate to the frame are taken off. Next, the nuts on the gland studs are removed, and the gland plate is slid back out of the way. The backplate is then removed and set aside. This exposes the shaft sleeve and the rotating element of the mechanical seal. Next, the shaft sleeve and the rotating element are slid off of the shaft, along with the gland plate. Then the mating ring is removed from the gland plate by simply pushing it out. After the collar set screws for the rotating element are loosened, the element is slid off of the sleeve. After a pump has been disassembled and its damaged mechanical seal has been removed, certain checks and measurements must be made before a new seal is installed. One of the first things to do is to check all machined surfaces for nicks and burrs. Minor imperfections can usually be removed with a light abrasive. Defects on the machined surfaces of the frame, the gland plate, the stuffing box housing, the shaft, or the sleeve could result in leaks and damaged components. But some pumps rely on metal-to-metal contact instead of a gasket or an O-ring to seal between the shaft shoulder and the sleeve. On these pumps, the surfaces should be lapped to remove imperfections that could interfere with creating an acceptable seal. To do this, the shaft key is removed and then lapping compound is applied to the shaft shoulder. Next, the sleeve is placed on the shaft and turned. After several minutes, the sleeve is taken off and the lapping compound is cleaned away. The surfaces are then inspected to make sure that proper surface contact can be made. There are other important checks that should be made before a mechanical seal is installed. Some of these checks involve the use of dial indicators. One important check is testing for shaft runout. A shaft that's bent or out of round can damage pump components and prevent a mechanical seal from operating properly. Before the measurement is taken, the dial indicator is zeroed. Then the shaft is rotated. The dial indicator should measure any shaft runout that's present. To determine if the runout is excessive, you'll need to refer to your company's policies and procedures or to the pump manufacturer's specifications. Next, sleeve runout is checked. Basically, this is done by installing the shaft sleeve in the impeller, which holds the sleeve in place, then repeating the process that's used for measuring shaft runout with a dial indicator. Checking sleeve runout is important because the seal's rotating element is mounted on the sleeve. Excessive sleeve runout could prevent the rotating element from being properly positioned next to the mating ring. Once the sleeve runout check is complete, the impeller and the sleeve are removed from the shaft again so that other checks can be made. One way to check thrust bearing wear is to mount a dial indicator so that the indicator stem is touching the end of the shaft. Then, after the dial indicator is set to 0, the shaft is moved back and forth, and dial indicator readings are taken to measure the total axial movement. Excessive axial shaft movement could indicate worn thrust bearings. Another important check using a dial indicator is checking the machined surface of the pump frame to see if it's perpendicular to the shaft. The pump backplate, which also forms the stuffing box where the mechanical seal components will fit, mounts directly to this frame, so the frame must be perpendicular to the shaft to prevent misalignment and seal damage. The frame is checked by mounting a dial indicator on the shaft so that the stem touches the machined surface of the frame. The dial indicator is zeroed, and a mark is made at the starting position. Then the shaft is rotated. 4 readings are taken at 90 degrees apart. If the frame and the shaft are perpendicular, the 4 readings should be the same. It's important to remember that any pump repairs that are necessary must be made before the mechanical seal is installed. Adjustments that are made after the seal is mounted could easily alter the position of the rotating element and cause the seal to fail. Now try answering some questions about checking pump components before installing a mechanical seal. In this topic, we've demonstrated a typical pump disassembly to remove a mechanical seal, and we've described various pump component checks that must be made to prepare for the installation of a new seal. To test your understanding of what we've covered, try answering some practice questions. Once a pump has been disassembled, the old mechanical seal has been removed, and the standard pump component checks have been made, installation measurements must be taken before a new mechanical seal is installed. Some of the pump components are reassembled temporarily so that these measurements can be taken. The measurements are used later to position the components of the new mechanical seal. Impeller clearance is usually one of the first measurements that should be taken. In our example, the rotating element of the mechanical seal mounts on a shaft sleeve. To begin reassembling components so that the measurement can be taken, the sleeve must be positioned onto the shaft. Care is taken to make sure that the sleeve is properly engaged on the drive pins or keys. An improperly positioned sleeve could be damaged when the impeller is installed. After the sleeve is in place, the pump backplate is positioned onto the frame. The match marks on the backplate and the frame are checked to make sure that the backplate is properly aligned. Once the backplate is in place, the nuts that hold it onto the frame should be tightened evenly. Next, the impeller, which holds the sleeve in place, is installed. Then the clearance between the impeller and the backplate will need to be measured. The clearance between the impeller and the backplate must be measured to make certain that the impeller is positioned correctly. The impeller holds the shaft sleeve in place, so if the impeller is out of position, the shaft sleeve and the mechanical seal components on the sleeve could be out of position as well. And if these components are out of position, the mechanical seal could fail. To determine the proper clearance between the impeller and the backplate, the pump manufacturer's specification should be checked. Then the gap between the impeller and the backplate is measured with a feeler gauge. And this measurement determines if the impeller is positioned properly. After the impeller clearance has been measured, the shaft sleeve is marked so that the rotating element can be positioned properly later. This is done by first applying bluing to the shaft sleeve along the edge of the stuffing box. Then a line is scribed in the bluing to mark the edge of the stuffing box. This line is a reference line for positioning the seal's rotating element. Once the line is marked, the pump components are disassembled again. First, the impeller is taken off. Then the nuts that hold the backplate in place are removed. And the backplate is taken off of the pump frame. Finally, the sleeve is removed from the shaft. And additional bluing is applied, this time along the length of the sleeve. Next, the seal manufacturer's installation instructions are checked to determine where the collar should be mounted on the shaft sleeve. The position of the collar is determined by using a measurement that's often called the location dimension. The location dimension is used to measure along the sleeve from the line marking the edge of the stuffing box. At that point, a second line is scribed in the bluing. This line serves as the reference line that helps to position the collar properly when the new seal's rotating ring is installed. Of course, there are some exceptions to the general procedures that we've just seen. For one thing, seals are not always mounted on shaft sleeves. A variation in the measurement procedure is associated with the location dimension for an outside seal. This type of seal is mounted outside the casing that's being sealed. So the second scribe line, which is used as a reference line for properly positioning the rotating ring collar, is made in the direction away from the impeller end of the shaft. Taking installation measurements is a critical first part of the procedure for installing virtually any type of mechanical seal. To make sure that you understand the information that we've covered, try answering a few questions. First, the mechanical seal components are inspected for defects or damage. These components include O-rings, a mating ring, and a pre-assembled rotating element. The new gaskets that will be used should also be inspected. Any parts that fail the inspection should be replaced. Next, a small amount of lubricant is applied to the shaft sleeve. Then the rotating element needs to be positioned on the shaft sleeve. The rotating element is slid onto the shaft sleeve, and the end of the rotating element collar that's opposite the seal face is aligned with the scribe mark that was made according to the location dimension. It's important to align the rotating element properly because the seal could fail prematurely if it isn't. Once the collar is positioned, the set screws on the collar are tightened just enough to hold the collar in place. If the set screws are over-tightened, the sleeve could become distorted and might not fit on the shaft properly. The screws will be tightened the rest of the way later when the sleeve is installed on the shaft. Many seal manufacturers use retaining clips like the one seen here to compress the springs and hold the parts of the rotating element together before it's installed. These clips can be removed after the rotating element has been secured to the sleeve. The next step is to prepare the mating ring for assembly into the gland plate. First, the gland plate is wiped clean with a cloth. Then the O-ring is installed onto the mating ring. Next, the gland plate is lubricated to make the mating ring installation easier. The mating ring has a polished side and an unpolished side. Most manufacturers mark the unpolished side of the ring to distinguish it from the polished one. The mating ring is inserted into the gland plate so that the unpolished side goes in first. Inserting the mating ring into the gland plate so that the unpolished side goes in first allows the polished side to face toward the rotating seal face when the rotating element is installed. The mating ring should be fully inserted into the gland plate, and it must not be cocked to either side. The gland plate can be turned over, and the back side of the ring can be checked to ensure that the ring is properly situated. After the mating ring is in place, all excess lubricant should be wiped off, and the mating ring face should be cleaned with lens paper and an approved solvent. Then the gasket between the gland plate and the stuffing box is positioned on the gland plate, and the gland plate is slid onto the shaft and pushed back against the bearing housing out of the way. Next, the rotating seal face is wiped clean with lens paper and an approved solvent. Then the shaft sleeve, which has the rotating element mounted on it, is slid onto the shaft. The gland plate should be supported while the sleeve is installed, and the sleeve should be pushed back all the way until it's flush with the shaft shoulder. It's also important to make sure that the keyway on the sleeve lines up with the pin or key on the shaft. The set screws on the rotating element collar, which were only partially tightened earlier, can now be tightened completely. Next, the back plate, which includes the stuffing box, is placed onto the frame. The back plate should be properly aligned with the frame match marks, and the stuffing box stud should align with the gland plate. Then the nuts that hold the back plate in place are tightened. Now the impeller can be readied for installation. On this pump, a small gasket is used to seal between the impeller and the shaft sleeve. Once the new gasket is in place, the impeller can be installed. Then the clearance between the impeller and the backplate should be measured and checked against the pump manufacturer's specifications to make sure that the components are properly positioned. If the clearance is correct, the gland plate can be secured. The plate is slid along the shaft toward the stuffing box. The gland plate nuts are then installed and tightened until the gland plate is snug against the stuffing box. Over-tightening these nuts could warp and damage the mating ring. To ensure that the nuts have been tightened uniformly, the gap between the gland plate and the stuffing box is measured at each gland plate bolt. If the gland plate is properly installed, the measurements should all be the same. In this part of the program, we're going to demonstrate how a couple of non-pusher type inside seals can be installed in pumps. First, we'll look at the installation of an elastomer bellows seal. Then we'll look at the installation of a metal bellows seal. The first step is to mount the collar. The collar is slid onto the sleeve so that the end of the collar that's opposite the seal face is positioned at the line that was scribed according to the location dimension. Next, the set screws are partially tightened to hold the collar in place. The spring is positioned on the sleeve. Then a small amount of an approved lubricant is applied to the outside of the sleeve, and the rotating ring is installed. As the rotating ring is placed onto the sleeve, the elastomer bellows makes contact with the lubricant and a bonding action occurs between the bellows and the sleeve. The rotating ring must be properly positioned against the spring as quickly as possible. If the rotating ring isn't properly positioned against the spring quickly, the bellows could become bonded at an incorrect position. Once the rotating ring has been positioned on the sleeve, the remaining steps are basically the same as the ones for installing most other mechanical seals. Generally, non-pusher seals that are equipped with elastomer bellows can only be used in moderate temperature and pressure ranges. However, there's another type of non-pusher seal that's designed for both low and high temperature and pressure ranges. That's a metal bellows seal. After the sleeve has been marked for the location dimension, the rotating element is placed into its proper position. Then the set screws are partially tightened to hold the collar in place. Since this collar uses a gasket to seal around the shaft sleeve, the cap screws on the collar are tightened to compress the gasket. These screws should be tightened in a crosswise pattern. The screws should be tightened in a crosswise pattern so that the pressure against the gasket is even. Next, the gasket for the mating ring is inserted into the gland plate, along with the mating ring itself. Then the gasket that seals between the gland plate and the stuffing box is placed on the gland plate, and the gland plate is slid onto the shaft. Now the shaft sleeve is positioned on the shaft, and the collar set screws are tightened the rest of the way. Next, the pump back plate is installed. Then the impeller is installed, and the clearance between the impeller and the back plate is checked to make sure that the components are properly positioned. Then the gland plate is bolted to the stuffing box. Next, the gap between the stuffing box and the gland plate is measured to ensure that the gland plate bolts have been tightened properly. Once that's accomplished, the seal installation is complete and the pump is ready to be reassembled and returned to service. To check your understanding of the procedures that we've covered, take a moment now to answer some questions. Suppose you're assigned to install an elastomer bellows seal in a pump. What should you do after you have positioned the spring on the sleeve, but before you mount the rotating ring on the sleeve? If you've been assigned to install a metal bellows seal in a pump, which of these steps should you usually do last? Now let's look at a demonstration of how a typical outside seal is installed, after the necessary preparations and installation measurements have been done. First, the rotating element is placed on the shaft and slid back against the bearing housing. In our example, no shaft sleeve is used, so the seal components are mounted directly on the pump shaft. Then the stationary element is prepared for installation. A gasket is placed in the gland plate. Then the mating ring is installed. On an outside seal, the polished side of the mating ring is installed so that it faces away from the stuffing box. Then a second gasket is installed, and the gland plate assembly is ready to be mounted onto the shaft. The gland plate should be slid back on the shaft as far as possible and positioned against the rotating element that was just installed. Now the back plate is prepared for installation. First, the bushing is inserted into the stuffing box and secured with a screw. Then the back plate is installed on the pump frame. Next, the gland plate is slid into position, and the cap screws that hold it in place are tightened. Then a feeler gauge is used to measure the gap between the gland plate and the back plate. The gap between the gland plate and the back plate is measured with a feeler gauge to make certain that the gland plate was tightened properly. Next, the rotating element is put into position so its collar is aligned with the scribe line that was made on the shaft when the location dimension was measured. Then the clamping screws are tightened. After the rotating element is in place, the impeller is installed and tightened. Then impeller clearance is checked and compared with the manufacturer's specifications to be sure that the components have been installed correctly. Once that's done, the seal installation is complete and the pump is ready to be reassembled so it can be returned to service. Because they're mounted outside of the pump casing, outside seals are relatively easy to install. Installation of our next example, a cartridge seal, is also a relatively simple process. The components are pre-assembled onto a shaft sleeve and a gland plate, so the seal is installed as a unit. This reduces the time required to install it. We'll pick up a cartridge seal installation after all the standard preparations have been made and the installation measurements have been taken. First, the cartridge is slid over the shaft and positioned so that the drive pin engages the slot on the cartridge sleeve. Then the back plate is aligned and positioned against the pump frame and bolted into place. Next, the gland plate is bolted to the stuffing box housing. Then the clearance between the gland plate and the stuffing box is checked at each bolt. After that's done, a new gasket is placed on the impeller, and the impeller is installed. The gap between the impeller and the pump backplate should be checked to verify that the components have been installed correctly. Then the set screws on the collar are tightened. In this case, the collar and set screws hold the cartridge sleeve to the shaft. Most cartridge seals have some type of device, such as this rubber bushing, that holds the rotating element in place and keeps the proper amount of compression on the seal's springs until the seal is installed. The bushing must be removed before the seal is put into service. That completes the seal installation. Once the pump is properly reassembled, plant procedures are followed to return the equipment to operation. Now check your knowledge of outside seal and cartridge seal installations by answering some questions. The bushing must be removed before the seal is put into service. That completes the seal installation. Once the pump is properly reassembled, plant procedures are followed to return the equipment to operation. To install any mechanical seal properly, you must carefully follow your plant's procedures and the recommendations of the seal manufacturer. There may be variations in installation procedures, depending on the type of seal being used and the equipment that the seal is being installed on, but the basic procedures that we've discussed should generally apply. So try answering some practice questions to make sure that you have a good understanding of the information that we've covered. There are many different mechanical seal designs and many methods for installing mechanical seals. The test you're about to take is based only on the examples and techniques presented in this program and does not account for variations that may exist. One of the first steps is separating the casing from the pump frame. To do this, the casing bolts must be removed. Then jacking bolts are installed to force the casing and pump frame apart. The jacking bolts are turned in a crosswise pattern to evenly dislodge the casing from the frame. Now the frame and the bearing housing can be moved to the side to allow for easy access to the remaining parts. The jacking bolts are also removed. Next, sleeve runout is checked. Basically, this is done by installing the shaft sleeve in the impeller, which holds the sleeve in place, then repeating the process that's used for measuring shaft runout with a dial indicator. Checking sleeve runout is important because the seal's rotating element is mounted on the sleeve. Excessive sleeve runout could prevent the rotating element from being properly positioned next to the mating ring. Once the sleeve runout check is complete, the impeller and the sleeve are removed from the shaft again so that other checks can be made. The clearance between the impeller and the backplate must be measured to make certain that the impeller is positioned correctly. The impeller holds the shaft sleeve in place, so if the impeller is out of position, the shaft sleeve and the mechanical seal components on the sleeve could be out of position as well. And if these components are out of position, the mechanical seal could fail. To determine the proper clearance between the impeller and the backplate, the pump manufacturer's specification should be checked. Then the gap between the impeller and the backplate is measured with a feeler gauge, and this measurement determines if the impeller is positioned properly. If the clearance is correct, the gland plate can be secured. The plate is slid along the shaft toward the stuffing box. The gland plate nuts are then installed and tightened until the gland plate is snug against the stuffing box. Over-tightening these nuts could warp and damage the mating ring. To ensure that the nuts have been tightened uniformly, the gap between the gland plate and the stuffing box is measured at each gland plate bolt. If the gland plate is properly installed, the measurements should all be the same.